Welcome back. Today we're going to take a look at Chapter 8. It's a beautiful day that I'm recording on. I've got my lucky Petoskey necklace on, so it's a good thing. And I love Petoskey stones. We camp at Petoskey State Park every year, and we have collected thousands of Petoskey stones. I have Petoskey gardens outside. I have Petoskey's everywhere in my house polished, and it's just fun. In any case, I've got my Petoskey stone necklace on today. Well, let's take a look at Chapter 8. And now Chapter 8, you've already done a non-graded introductory worksheet that gets you started with metabolism and energy. So we're going to skip ahead to here, and we're going to focus today on, in this video, on spontaneous and non-spontaneous reactions. To do that, we have to start here thinking about energy. You've learned about what energy is and different forms of it. When we talk about reactions, we're interested in knowing if a reaction is going to be energetically favorable, if it's going to run on its own, or if it's going to require an energy input. In order to talk about reactions, we need to have some sort of concept that can explain the energy in chemicals and the energy in the reaction. And we use the concept of free energy created by a person named Gibbs. So free energy symbol is G. G is the energy available by the cell to do work, or the energy of the system. We can talk about free energy as equal to the total energy available by the system minus an entropy factor, because there's always entropy happening. We're really interested in using this concept of free energy with respect to reactions. So like, let's say I wanted to build glycogen. Glycogen is a complex molecule made up of hundreds or thousands of glucose molecules. So it's a big molecule. I can think of that as like a big long slinky, right? Made up of many little glucose molecules. The glucose molecules are maybe like the Titan slinky put together, and you make one big, long, stretched out slinky, all right? We want to be able to think about, does this reaction happen, does the building of a glycogen happen spontaneously or non-spontaneously? Does it happen without any extra energy added, or do we have to add extra energy to it? And what we like to say, and this is an important reaction here, is we can take a look at the reaction and we can look at the change in free energy. If we measure the free energy of the reactants and the products, and we look at how that free energy changes. So if we take the free energy of the products, the energy that the product molecules have, minus the free energy of the reactants, the change in free energy is going to help us understand whether a chemical reaction is spontaneous or non-spontaneous. So let's take a look. So spontaneous reactions are also called exergonic reactions. Exergonic reactions. Exergonic or spontaneous reactions are energetically favorable reactions. So these reactions actually release energy. Release energy. And in this situation, molecules move from less stable to more stable. More stable, move to more stable positions. I don't know how those lines form sometimes in my writing here. But we would say that the molecules are moving from a less stable to a more stable position. So something like a less stable slinky to a more stable position. So less stable would be stretched out, more stable would be closed up. Or less stable would be at the top of the stairs, more stable at the bottom of the stairs. Okay, what we say in this case is that the free energy of the system decreases. Delta G, or the change in free energy, is negative or less than 0. Let's take a look at some examples, and then I'll draw this out to help us understand. So a spontaneous or energetically favorable reaction could be any one of these things shown. Oh, we can go back to our diver. Our diver, as he dives, he has, actually I should start here. At the top of the platform, this diver has a lot of potential energy because of his position, right? Then he dives and he lands in the water. This reaction is a downhill or energetically favorable reaction. The diver goes from a less stable to a more stable place. Okay? It's energy releasing. And that energy that's released can be used to do other things. Diffusion is another example of the movement of molecules, the spreading out of molecules, the movement from a high energy to a lower energy position, a less stable to a more stable position. Chemicals also, because of their structure, have potential energy or have free energy. And a chemical, in this case, a big complex chemical that is being broken into smaller pieces, is moving to a more stable location. The individual pieces are more stable than the big complex structure was to begin with. And when that happens, we say, hey, this is a spontaneous reaction, a reaction that is going to run without extra help, if you will. Another way to think about this is to draw a bar graph. It's pretty simple. If we look at the free energy as a function of the reaction progress, okay, in a spontaneous reaction, the reactants have high free energy. Reactants. Okay, they're unstable. They may be big, complex, unstable. They have high free energy. The products have much lower free energy. Okay? Like this. And so there's a change in free energy. This amount represents the change in free energy. There's a drop in free energy. Delta G is going to be negative because if you take the free energy of the products minus the free energy of the reactants, you're going to get a negative number. So delta G is less than 0, and this is an example of a spontaneous reaction. This reaction is a downhill reaction. It's a spontaneous reaction. It's going to happen without outside help. Doesn't mean it's going to happen fast, but it's going to happen without outside help. That's how I draw a spontaneous reaction. Here's another picture of it well drawn. What we have here again is the free energy as a function of the progress of the reaction. Reactants have higher free energy than products, and so we see a drop in free energy, and that's the amount of energy that actually is released by the reaction. As the reaction proceeds, that's the energy that's released. Here's an example of the hydrolysis of ATP. Okay? This is something we're going to think about a lot, actually. ATP is a complex molecule. It's up here. There's the picture of it. It looks a little bit like a nucleotide. It has ribose, adenine attached to that ribose. So we've got a 5-carbon sugar attached to adenine, and then attached to the 5-carbon sugar is also a set of 3 phosphate groups. See those little yellow circles? Yellow circles with P's in them. That's how we always draw phosphate, right? This molecule is the currency for how our cells do work, right? ATP. Hey, ATP is how we do all of our work. We think of ATP as a great source of energy. Well, ATP can be broken down. We use the term the hydrolysis of ATP to describe that breaking down because we need to add water to break a bond, and we end up with 1 inorganic phosphate and ADP. The hydrolysis of ADP looks like releases energy. So what does that tell us about this reaction? Is the change in free energy, is delta G less than 0 or more than 0? So we think about the reactants in the products. The reactant, ATP, has high free energy, okay? The products, ADP and phosphate, have lower free energy. There's a drop in the free energy from reactants to products. This becomes more stable. The products are more stable. We've got a release of energy. Delta G is less than 0. The question is, why does ATP have so much free energy? And that's a good question to ask, because we know it does. We use it all the time in our cells to do work. The hydrolysis of ATP is used to do work because it releases energy, right? Well, why does ATP have so much free energy? It has to do with its structure. It's unstable. Think of it as a slinky stretched out, or a slinky at the top of the stairs. It's unstable because it has 3 phosphates right next to each other. All of them have negative charges. They don't like to be near each other. It's going to be really easy to break one of those phosphates off and make the molecule more stable. Okay? In any case, the hydrolysis of ATP represents a spontaneous reaction where delta G is less than 0. Non-spontaneous reactions are essentially the reverse. These reactions are called endergonic reactions. E-N-D-E-R, gonic. Endergonic reactions in biology. And these reactions are going to require or absorb energy. So we can write down require or absorb energy. And in this system, the products have more free energy than the reactants. The free energy of the system is going to increase. Delta G is going to be greater than 0. Let's take a look at a diagram of that, and then we'll think about that example as well. Okay. I like the bar graph. This is my favorite way to think about exergonic and endergonic reactions, because I can just picture it and I know what's going on. So here we're looking at free energy and the progress of the reaction. Our reactants here have low free energy, and our products are much less stable, much higher free energy. Well, in order for this reaction to happen, we have to add free energy here in order for the reaction to happen. That's the amount of energy that's required. If I calculate delta G is equal to the free energy of the products minus the free energy of the reactants, remember. You're going to get a positive number. So I'm going to put is equal to or greater than 0. Okay, you're going to get actually I'm just going to put greater than 0. Okay? Which has higher free energy in an endergonic reaction. The reactants or the products? Well, the picture shows us the products do. This reaction, let's see, what did I say? The reaction of the making of sucrose from glucose and fructose is a non-spontaneous or endergonic reaction. So if we want to build the molecule sucrose, that's table sugar, right? And it's made up of glucose and fructose. The glucose molecule and the fructose molecules are pretty stable. They're small, they're stable, and they have low free energy. The sucrose molecule has higher free energy. This is sucrose up here. Okay. And we're also going to have water up here because this is going to be a dehydration reaction. In any case, to build sucrose, it's going to take energy. This is an endergonic, energy-requiring, non-spontaneous reaction. Now, inside a cell, the cell does a really good job of coupling exergonic and endergonic reactions together, because if you're trying to build some complex molecule, where are you going to get the energy to do it? Well, you're going to get the energy from an exergonic reaction. And that exergonic reaction is often the hydrolysis of ATP. We use the energy released as ATP is hydrolyzed to do work in the cell, to build bigger, more complex molecules that require endergonic reactions. Here's an example of a coupling of an endergonic with an exergonic reaction. So it's kind of a strange drawing. We're thinking about doing chemical work here. We're doing chemical reactions, right? And what we've got here is we're trying to build glutamine Glutamine is an amino acid, and to build it requires adding glutamic acid to ammonia. Putting an ammonia on glutamic acid makes glutamine. But when I see this reaction, I'm like, uh-oh, this is an endergonic reaction. It's going to require energy. In fact, it's going to require 3.4 kilocalories per mole of glutamine. That's how we write it down. So delta G is positive. How am I going to get this reaction to run inside a cell? Couple this reaction with the hydrolysis of ATP. Now we know that the hydrolysis of ATP, right, the breaking down of ATP is exergonic. It's energy releasing. Delta G is negative. That's energetically favorable. If we can couple the making of glutamine with the hydrolysis of ATP, and we do the math here, we realize that together the overall reaction is energetically favorable because delta G is negative. And that's how we do this. Now, when we couple reactions together, it's not that these reactions are just sort of happening side by side and somehow energy sort of swims from the hydrolysis of ATP over here to the making of glutamine. There's actually, the hydrolysis of ATP kind of happens in conjunction with the making of glutamine. So in this picture here, you can kind of see how it happens. We've got the reactants, glutamic acid and ATP. And what happens is a phosphate from ATP gets attached to our glutamic acid. Now we have ADP as a leftover. Then that phosphate is quickly replaced with what we want, the ammonia group added to it, making glutamine and the leftover products of the hydrolysis of ATP. Either way, we've got, when we couple the exergonic reaction of the hydrolysis of ATP with the making of glutamine, with this endergonic reaction, we can get an energetically favorable set of reactions, and that means we can do it. And that's what the cells do with the hydrolysis of ATP. By the way, the hydrolysis of ATP also drives mechanical work in the cell and transport work, not just chemical work. ATP is amazing. Oh, and as a quick digression, I want to talk about ATP just a little bit more. We're going to get into it in Chapter 9. But ATP is the currency by which our cells do work, and we are constantly using it. We're breaking it down, right? We're taking ATP and hydrolyzing it, using water to break it into its components. But that's great because that releases energy that we can use to do work, right? This part of the reaction here is exergonic or spontaneous. I can't write that all in there. You put that in. But we need to recycle our ATP. We need to make more of it all the time, right? Because we want to use it. So we need to somehow rebuild our ATP. Right? Rebuilding our ATP is not spontaneous. It's non-spontaneous. It's endergonic. It takes energy to rebuild, to recycle our ATP, right? It's kind of like if you wanted to think about the rebuilding of ATP, you've got, you've got ADP down here, plus its inorganic phosphate, and ATP up here. ATP has higher free energy. So to build it, it's going to take some energy. Where are we going to get that energy from? We're going to get that energy from the food that we eat. The nutrition that we eat is used, the energy in the food that we eat is used to rebuild ATP all the time. And by the way, this is Chapter 9 material. We're going to talk about how do we rebuild ATP, taking the energy from the food that we eat and using it to make ATP. This would be, by the way, super exciting. We're going to spend a lot of time on that in Chapter 9. Okay, that's the end of this video. So let's turn it off.